Okay, so now we're going to start looking at convolutional networks. I'm going to dedicate more time to this later on, but this lecture will be a brief introduction to convolutional layers and the application of these layers in convolutional networks for classification in particular in this lecture. And we're also going to look at the Karash sequential interface. The reason for this is that convolutional layers now start to become quite a bit more complex to implement than just the dense layers that we saw, and it's not worth the problem of trying to do everything at a low level using basic TensorFlow operations. So we're going to start using Keras, where you can just create your networks by adding in sequence the different layers that we need. So this is the sequential interface in Keras. Then we're going to look at the functional interface in future lectures, but we're going to start with this simpler one. So I'm going to explain what is a convolution mathematically and what it's used for, and then we're going to look at its use in neural networks. In particular, I'm going to use as an example image classification, but convolutional layers can be used for data series, for processing, basically for identifying patterns, whether in 3 dimensions, in 2 dimensions, or 1 dimension, doesn't matter. You can use the same kind of things. I'm going to look at some different layers too, for example, pooling for reducing the resolution of the input and basically converting this into the filters that we are trying to extract. And we're going to see how convolutional networks can be used for classification. And then I'm going to talk a bit about the tutorial for today, so using convolutional networks for classifying the fashionist dataset. A convolution operation is when we are computing the convolution between 2 functions for time t. The convolution operation is this integral over all the universe for the product of the 2 functions, where one of them is shifted by t and inverted in the x-axis. So basically this is the equation here. We're going to integrate over tau over all the input as a function of tau, but we are shifting this g function by t, and then we are going to use minus tau in the input to that function. And this is when we define convolution in this way, it's commutative. We can do the convolution of f with g or g with f, and it gives us the same result. So basically this inversion here is to make things commutative, and we are integrating the product of the 2 functions where one of them is shifted by some value of t. And now the convolution of this for a particular value of t is this integral. And now we can compute the convolution for different shifts and obtain the profile over all the t. This is used, for example, in physics for linear time invariant systems, which are systems that respond linearly to some impulse, to some effect, perturbation of the system, and the response is invariant over time. For example, imagine that we have an iron bar that when we hit it with a hammer, it starts to oscillate, and then the oscillation dampens. We can assume this as a linear response, meaning that if we hit it twice as hard, the amplitude will be 2 times greater. And it's time independent in the sense that if we hit it at time 0, it has this profile, but if we hit it, for example, at times 2, it would have the same profile just starting at times 2. So it doesn't matter when we are computing the time, the iron bar will oscillate always at the same time. So one way of using convolution here would be to figure out what happens if we hit the iron bar very fast, twice with a hammer, for example, with an interval of 0.2 seconds, and we hit it twice with this intensity. What would be the oscillation of the iron bar in this case? We can use convolution for that. We take the symmetric of the response function. So this is basically the same thing, but shifted around, because we are using this minus here. And then we compute the product with different time shifts. So before we give the impulse with the hammer, nothing happens over here. But then when we hit it twice, we have this shape of the oscillation of the iron bar. So this is one example of using convolution to figure out what happens to the response of the system, in this case the oscillation of the iron bar, when we hit it with a more complex pattern, for example, these two hammer strikes in a quick sequence. Okay, so this is not something that we are very interested in neural networks, but this is just to give you a more intuitive understanding of what convolutions can be used for. But we can think about this in reverse. Suppose that we have this strange signal that we read from some, say, radio transmitter, something like that, and we want to detect this particular pattern of spikes that occurs inside the signal. What we can do with a convolution, we create a detector function. So basically it's the same pattern but inverted on the x-axis here. And now we compute the convolution. So as we compute the product at different time shifts, we get this slight oscillation here. But when we start getting a match between the pattern and the signal, we start having these larger peaks. And the largest peak corresponds to the time where the pattern exactly matches the signal. So you can see here the result of the convolution at different time shifts gives us a way of detecting the match between these two patterns. If the output of the convolution is high at some specific time shift, we know that we found something very similar to the pattern that we are looking for. And this is actually an application that interests us more in neural networks. We are basically using convolutions to identify patterns in the data. So what we can do here, this is the definition of the convolution for continuous functions, but we also can use the same for discrete convolution. This is basically a sum of the product of the discrete functions over the different steps. And we can imagine that one of these functions is something that we are creating to identify the pattern. So this is the kernel that we have here, that we are using to identify a particular pattern in the data. And this kernel has these different weights that we can adjust, and the weights will determine what kind of pattern the kernel is responding to. So you can imagine that this particular profile here is created by using some specific weights at these points, 0 everywhere else, and this way we can create this kernel to respond in particular to that specific pattern when we shift the kernel in order to superimpose the pattern. So this is what we're going to use for convolutional neural networks. So in practice, we are not going to compute the sum over minus infinity to infinity, because we can have a finite number of parameters in our kernel, but this is just the same as assuming that all the other infinite weights are 0, and we can just focus on the ones that are not 0. So we can have a small kernel that only looks at a small window by assuming that everywhere else it's 0. So these parameters are a small set of parameters that will be learned in the network. So this kernel is actually like a neuron that is being trained, and during training the neural network will find the best set of parameters to identify useful patterns to minimize the loss function, for example, to classify the image. The output will also be a tensor, and typically, depending on the padding and things, we're going to look at that in a bit more detail in a while, but in general it will have the same shape as the input, because we are sliding our kernel over the input. So imagine that this was a vector with all these values of the signal. So this was the vector that was input into the network. We have this kernel for detecting that pattern. We are sliding it over the input, and this would be the feature map that we get at the output. It has the same size as the input, but it gives us the response of the kernel to each part, to each region of the input vector. So this is basically what we will do with the convolution networks. We give the input to the convolution layer. The kernel, we can imagine it sliding over the layer or being applied to all over the input and producing a feature map on the output that has the same size as the input, but now outputs the response of the kernel to the different regions of the input. So one particular detail here in convolution, we have a commutative operation where we can use the input and then multiply by the kernel, and we are indexing the kernel in this way. So we consider the whole input and then index the kernel. We can do this the other way around. So basically we can imagine this as using always the same kernel without changes in indexing, but pointing at different regions of the input. Since convolution is commutative, we can imagine things either way, so it doesn't make much difference. And basically, this would be perhaps the more intuitive way of imagining this. We imagine that the kernel is just this small window here, and when we apply the convolution operation, we are sliding this small window over the input and registering the result of the products that we are getting. So basically we are keeping always the same indexes for the kernel and just shifting the indexing of the input values in the vector. Another thing is that in convolution we have this inversion here using the negative of the variables over which we are computing the integral, because this is what makes convolution commutative. But this is basically the same as simply inverting the kernel over those variables. So this would be just an additional computational complication that we can do away with. So in practice, what we do with convolutional networks is we just apply the kernel and we slide over the input without doing those inversals in these axes, because that is simply the same as flipping the kernel originally or something like that. So we ignore that, and this means that if we are being rigorous when referring to this operation, this is actually a cross-correlation function and not really a convolution. So the convolution has this symmetrical operation here, so inverting along this axis. The cross-correlation does not do that. So strictly speaking, it would no longer be commutative, but we don't really care about this because all of the weights in these kernels will be learned during the network, so it doesn't matter if it's learning them in the reverse order or something like that. If it was to be a convolution, we are just simplifying the operations. So basically, this is what we are doing in a convolution network. We are sliding the kernel over the input and computing for each particular shift these sum of these products, so basically the response of the neuron there, and we are producing a feature map with the result of these operations for all the possible shifts over the input. Okay, so let's see how this works in a convolutional neural network. We can imagine this as being an adaptation of the dense networks, of the fully connected layers, in order to reduce the number of parameters that we need to find the patterns we want. So there are two attributes here for that. There are sparse interactions, sparse connectivity between the layers. We don't have as many connections between the input layer and the outputs of the current layer, and also we are sharing parameters along the layer, which gives us fewer parameters, independent parameters to adjust. This gives the convolutional layer this property of equivariance to some transformations. This means that a transformation in the input to the convolution layer will result in the same transformation on the output of the convolution layer. We can imagine this easily here. Suppose that the pattern we are looking for, instead of being here, we had everything shifted a bit to the right. The result will simply be shift the output of the convolution a bit to the right. So the same transformation here will also apply to the output. And this is what equivariance means. It changes in the same way. Note that if we were connecting these two with a dense layer, this would not necessarily be the case, because a shift here would make different neurons respond to different inputs and could change completely the output of a dense layer. But with a convolution layer, we have this property of equivariance. So what does these things mean? The sparse interactions is this difference between having a dense layer where each neuron on the second layer here would have connections to all the neurons in the input layer or in the previous layer. So we would have lots of connections here, but with a convolutional layer, what we are doing is we are using a narrow window, which corresponds to the receptive field of our kernel. And we are assuming that everywhere outside this window, the weights are 0, so we don't even store them. And this means that the connection between different layers is much sparser. Our kernel is only looking at those in this short region and not to all the inputs. We also have weight sharing. Oh, by the way, this means that with a single convolutional layer, each neuron is only looking at a small part of the input. However, we can, by adding more layers, make it so that this particular neuron here, so this would be an abstract neuron. In fact, we are just sliding the kernel, but the output at this point could be dependent on the large receptive field on the inputs, because it's depending on the output of previous convolutional layers that include outputs that depend on different receptive fields here. So basically, this works in a bit like a pyramid. Even though each of the outputs on the convolutional layer is depending on only a few of the inputs to that layer, by stacking layers we can reach wider and wider regions on the input data. So this means that the receptive field of one neuron in a convolutional layer can be large in the original data, in the input, because of what's happening in between in the other layers. We also have this parameter sharing because since we are using the same kernel, when we have a dense network, like in a multi-layer perceptron, then the weight, for example, connecting this input to this neuron is different from all the other weights. But if we are using a convolutional network, since the kernel is the same, the weight that connects this input to this neuron is the same as the weight that connects this input to this neuron, and so on, because we are in effect sliding the same kernel over the inputs to produce all the outputs. So it's always the same weight there, it's always the same weight in this diagonal here, it's always the same weight in this diagonal here, and so on. So we are sharing these parameters. This means that a convolutional layer can have a lot fewer parameters than a dense layer, and not only because they are shared over all the region of the input, but also because they are much sparser and we don't have all the possible connections. So let's see an example. Suppose that we want a kernel to detect edges from left to right, for example. Then we can create a kernel with two inputs, with two weights, one -1 and one +1, for instance, and we can multiply the inputs by these weights of two adjacent pixels, one on the left of the other. And then we would, by sliding this kernel over all the image, we would get a feature map that would tell us when the image changes from white to black, we detect this edge here, and then again when it changes from black to white, and so on. So we have these different values, negative or positive, that detect these different edges by sliding this kernel over the image. Of course, this would be a very simple example, but this is the idea of what we get in the output of a convolutional layer, depending on the input to the layer and the kernel that we're using. And the equivariance property would be that by shifting, for example, if we shift the dog a bit to the side, then we get a shift of the feature map to the side. There are some operations that are not necessarily equivariant. For example, rotation could give us a different result, but in translation, convolutional filters tend to be equivariant. So translations in the original input will result just in translations in shifts in the output feature map. So this is a representation of what's happening in a convolutional layer. Since we call this receptive field to the region where the visual cortex neurons respond to, so we have these neurons in the backside of our brain for the visual cortex, and each neuron fires in response to stimuli over a small region in the retina. And this is called the receptive field of the neuron. With an analogy to that, we call the receptive field of some kernel, some neuron in a convolutional layer, we call the region in the input that particular output corresponds to. So this will depend on the size of the kernel. Of course, it will also depend on the intervening layers, but if we consider the first convolutional layer, we can have something like this. Each of these circles represents a different kernel, so the output of a different kernel, and each kernel will have weights for a small region of the input. So if we apply these 5 kernels, we will have 5 output values for this region of the input. But each kernel will be applied over all the range of the input. This could be, for example, a grayscale image. And so it will generate here this stack of 5 feature maps, which with each one the output of the kernel sliding over all the input. And the output is computed like this. We have the weights of the kernel here in red. They are multiplied by the inputs and they are added together to give the result of the feature map. So this would be the output of the feature map of one of these kernels, and another of these kernels would have different weights and give us a different feature map, and so on. And this would be a typical convolution layer where we convert the input into a number of feature maps by applying a number of kernels. Note, however, that we are applying this to the whole image, but always with the same number of weights. So in this case, each kernel only has 9 parameters, which are the weights, and they are applied always the same through the image. So basically, if we have 5 kernels with 9 weights each, we have 40 weights for this layer, this convolutional layer in this case. Then we're going to create this output. So basically the height and width would be depending on the size of the input image. The depth would depend on the number of filters that we're applying. So for one example, we would get this 3-dimensional tensor for the output at that convolutional layer. If we are using a mini batch, then typically these, in the case of image classification, these tensors will have 4 dimensions or more because well, we'll have 4 dimensions, and they can have 4 dimensions here at the beginning too, because if the image is in color, then we don't have only one matrix of inputs, we have 3 for red, green, and blue, typically in color image. So we are dealing with these 4-dimensional tensors, which have 2 dimensions because of the 2-dimensional matrix of the image. The 3rd dimension corresponds to the different channels, either the different colors in the beginning or the different feature maps that are being generated. And the 4th dimension corresponds to the batch, because now we have one 3-dimensional matrix for each example in the mini batch that we are giving the network. So this would be, for image classification in general, the shape of the tensors that you'll get. Since the convolution is a linear operation, we also include in convolutional layers activation function to give us a nonlinear response. Otherwise, stacking these layers would not make sense. So typically, we use rectified linear unit or some variant of that to improve training, and we keep stacking these convolutions, activations, and then feed into the next convolution layer and so on. Now, there are some parameters that are important in the convolution. The depth of the convolutional layer is just the number of filters we are using. So how many kernels we are using for that particular layer. And this will determine the depth of the output of that stack of feature maps. The stride is the jump of the kernel when we are computing the different convolutions at different shifts. So for example, here we have a stride of 1. We are shifting by 1 and computing each value. Here we have a larger stride, and in this case we are shifting by 2. So we have fewer values on the output. And then we have padding. In this particular example that I showed here, there is no padding. So when we shift the kernel over the input, we actually get a smaller output, even though we are using a stride of 1, because we cannot move outside the region of the input. So we cannot get 5 values here. We can only get 3 because we only have 3 positions when we shift to the side. We can avoid that and use padding. For example, fill with zeros. Imagine that the input is padded with zeros, and this allows us to shift the kernel over all the region of the input. And this allows us to make it so that the feature map that outputs from this convolution has the same dimensions as the input to the convolution. So we are preserving the dimensions when we use padding in convolution. If you don't use padding, then you have this slight shrinkage from layer to layer, and you need to take that into account when you are trying to fit things together in your network. So this would be an example for image classification. We have a convolution layer here that gives us a set of feature maps for the image. Then we have different feature maps here. Then we apply rectified linear unit activation. So these are the actual feature maps that are produced after activation. And then we again do a convolution on these outputs, and we have rectified linear unit. So we produce these feature maps here, and then pooling. Pooling serves to shrink things down. I'm going to show this in more detail, but basically we are downsampling these feature maps so that we shrink the resolution. And now we do again convolution, shrink the resolution with pooling, and so on. And then we pass on to dense networks. But this is typically how we stack things. Convolutions and occasionally pooling. We can use convolution and pooling, or we can stack different convolution layers before we do pooling. The reason for that is to increase the receptive field without increasing many parameters. So look at this way, we can use these kernels that only have 3 inputs. So basically each kernel only has 3 parameters, 3 weights here, and we can have a receptive field of 5 in length for this particular neuron here by having an intermediate layer of convolutions. So this one has 3 parameters, this other layer has 3 parameters, and we need to only have 6 parameters in this case. So if we start increasing, especially in 2 dimensions, 3 dimensions, and so on, if you start increasing the size of the receptive field in the same convolution layer, you can increase the number of parameters much faster. For example, if this was in 2 dimensions, we would need 25 parameters for one single step using a receptive field of 5, so it would be 5 by 5. If we use this in 2 steps with receptive fields of 3, we only use 9 parameters for each step, so that's 18 instead of 25. So in general, when you're using things in 2 dimensions, it allows you to keep the network simpler with fewer parameters by stacking convolutional layers with smaller receptive fields or smaller size on the kernel, the window of the kernel, instead of just having one layer with a larger window. That would give you more parameters to adjust. So this is a typical convolutional architecture. Now, the pooling is actually very simple. We have these convolution layers that are producing the feature maps. We apply the nonlinear activation, but then we may want to reduce the resolution, the size of those feature maps, in order to keep shrinking and the number of values that we're using, and making a kind of a pyramid until we reach the stage where we do the classification, for example. And pooling is simply taking a region of the feature map and using some aggregation function. For example, with max pooling, we take the maximum output of the feature map on each region, and now we can downsample from this resolution of 4x4 into this one of 2x2 by taking the maximum of this window, the maximum of this window, and so on. So this would be the example of max pooling. We can use other types of pooling, average pooling, L2 norm, which uses the square root of the sum of the squares, and so forth. There are different aggregation functions, but the idea is always the same. We're going to pool the data in order to generate an output that aggregates these values. Generally, we want to do this to reduce the size of the feature maps we are dealing with. So to compute pooling, we can change things. We can change the window, the size of the window. We can change striding. Typically, stride will be the same as the size of the region. So stride is the size of the step we are taking here, and this is the width of the pooling window. And if this is 2x2, then we are going to use strides of 2 so that we don't overlap the pooling. But you can do many combinations of this if you want, but this is the most typical application. Will be use a stride equal to the size of the regions and use pooling to reduce the dimensions of the feature map. So this would be an example. AlexNet, we saw this one briefly before. We have these convolution layers. We have max pooling between these layers. And then we have at the end a set of dense layers, so multi-layer perceptron, until we reach the classification. So this would be a change where we shift from the feature maps and the kernels into a dense layer or a stack of dense layers, so that then we train the classifier. And you can imagine that these convolution layers are learning how to extract useful features from the images, and then they are feeding in these features into the classifier that has this this architecture like a multi-layer perceptron, and then outputs the classification there. So this is how we're going to use convolutional layers for image classification. So this is what we're going to do in the tutorial, and we're going to use the sequential API in Keras. What you need to do is you're going to import from Keras one optimizer. We can start with SGD, but you can experiment with the others that we talked before. We need the sequential model here, and then we can import different layers that we're going to experiment. Pooling, convolution in 2 dimensions, patch normalization, and so forth. So you can import these classes. And now the way this works is you create your object of the sequential model, and then you just call the add method to add particular layers. For example, if you want to add a 2-dimensional convolutional layer, you can specify the number of filters, so the number of feature maps that it will output, and the dimensions of the kernel. This will be 3x3, the kernel size. You can specify the padding. I'm using the same padding, same in this case in Keras, means preserving the same dimension on the output. So it's this kind of padding that we saw here, where we put zeros around so that the output has the same dimension as the input. I think this is the default, so strictly speaking, you don't need to specify this one, but check the documentation because sometimes the defaults change. And so we have this padding. And for the first layer that we are adding, we need to specify the shape of each example. Note that this is not the shape of the batch. There is an additional dimension here that Keras will handle depending on the number of examples you add in the batch, but this would be the shape of the example. And in this case, we're going to use the fashion NIST dataset. So these are grayscale images. They are just 28 by 28, but a two-dimensional convolution layer expects to have three-dimensional inputs because the first two dimensions are the size of the image in this case, and the third dimension is the number of channels that we are inputting. So if we have a grayscale image, it's only one channel, it's only the intensity of the pixel. If you have color images, this will be three channels, red, green, and blue. So we just specify the shape of the input. And we only need to do that for the first layer, which is the one that will receive the input data. The other layers we can just add without specifying the shape because Keras automatically will compute the shapes as needed for matching the layers together. So now we can add an activation, rectified linear unit. We can add then more convolutional layers, max pooling, and so on. And then so there are parts here that are missing. I'm going to describe the model. You can try later, but this is just to show you a bit of code how to implement it. Sorry. And then when we are going to pass to the dense part of our network, where we're going to do the actual classification, we have to move from these two-dimensional inputs into, or three-dimensional in this case, into a single-dimensional vector to input into the dense layer. In order to do that, you need to add this special layer, which is the flatten layer. This one just does the reshape of the outputs. So this is similar to what we did when we were implementing those multi-layer perceptrons, where we used reshape on the output of the predictions, for example, so that the vector would match the labels. But in this case, we are doing this reshape to the output of the convolutional layers, which are multidimensional, in order to have everything in a single dimensional vector to input into the dense layer. And now we can add a dense layer, the activation, and for example, you can put batch normalization, dropout, and you can try these different techniques that we saw. So in this case, a dropout of 50% here. Then we have an additional dense layer of 10 because we are classifying these images into 10 different classes. So the fashion NIST, you can look it up online, is similar to the NIST problem that we used last week, where we have the digits, but these are cartoons of different types of clothes, shoes, and so on. It's a bit more difficult to classify, so that's why we are using the convolutional networks in this case. The other one is very easy to classify. But it has the same size and the same number of classes, so we also have a dense output and the softmax activation. So this is basically similar to what you did last week when classifying NIST with a multi-layer perceptron. The difference is that we are using these convolutional layers here and we are using Keras. So we don't have to worry about those small details of using softmax activation for prediction, but then using the log hits for the optimization and so on. Keras takes care of that automatically. So you just need to set your model and then compile the model to run it. So basically, you create the model like this, add all the different layers, and then you also create an optimizer, and then you compile your model. You specify what kind of loss function you want to use, what optimizer you're going to use, and what metrics you want to see output during training. So this is basically what you do to create the model using Keras. And now you can call fit to train the model. You can use your training set, you can use your validation data. In this case, I use the test set for validation because I don't particularly care about estimating the error at the end. But if you want, you can experiment with this and do different combinations. You specify the size of the batch, the number of epochs, and so on. And then you can do this, you can save the weights. I recommend that you do this because in about 2 weeks, we're going to reuse these weights with transfer learning. So you can, if you want, you can use the actual weights from your training session. So this saves the weights of your model. You can also load the weights by using load weights after compiling the model if you want. So you can recover the weights that you saved in training. There are some notes here about the use of batch normalization and dropout, because in theory you could put this everywhere, but in some cases it can give you bad results and it's a bit weird. So batch normalization you should generally use after the activation function, because the idea is that we are standardizing the input into the next layer. We have a layer of 512 neurons, and then we are inputting the output of this layer into this layer of 10 neurons. If we want to standardize the input to this layer, we should add batch normalization after the activation function. Otherwise, the activation function will shift the mean and the standard deviation and will not have standardized inputs. So this is the general consensus, although it may be that if you look at the internet, some people do it in reverse and there is some argument about that. But this, I think, is what makes most sense and in general works better. So use batch normalization after activation. In general, it's not a good idea to use dropout before batch normalizations. The reason for this is that batch normalization stores the average outputs during training. The average, so the mean and the standard deviation, so that it can rescale everything afterwards when we are using the network for doing predictions. But dropout after training rescales all the outputs to compensate the disabling of the neurons with some probability during training. So the interaction between the two can mess things up a bit, because batch normalization took all the statistics during training and now suddenly everything is, for example, twice as large because dropout recalibrated the output. And now batch normalization will not be working very well. So generally, the recommendation is that you use dropout only after all the batch normalizations that you have. Another important thing when dealing with convolution networks is that although you can use dropout in convolution layers, it has a different impact than it has in dense layers. So in dense layers, what we saw is that dropout is creating implicitly different networks with different combinations of neurons. But with a convolutional layer, dropout is switching off pixels on the feature map. So it's blinding the next layer to some points in the image at random. This may be of some benefit in some cases, so you can experiment with dropout in convolution layers. Don't use a very high probability though, because otherwise you are blacking out most of the feature map and that may not be a good idea. But it's a different thing than what we are doing in dense layers. It's not a kind of ensemble learning or bagging, something similar to bagging. It's just blocking out some parts of the image, which can be beneficial to prevent overfitting, but it's a different thing conceptually. So in this case, I leave up to you if you want to experiment with dropout in the convolutional layer, but I recommend you try batch normalization and dropout in the dense layers at the end here. Okay, so to monitor the model, you can check the architecture of the model by calling summary. This prints out on your console all the layers and the sizes and the number of parameters and so on. And you can also create callbacks to the TensorBoard. You can use this Keras callback class here, the TensorBoard class here, where you specify your log dir and so on. And you create this callback and then you give this to the fit method, you can create several callbacks and just call them. So this one is just a default that creates the graph and plots the whatever metrics you chose to register during training. So if you want, you can use TensorBoard. Otherwise, you can just also look at the console, because the fit method will print out at each epoch what it's doing. So usually that is enough, but it's also easy to use TensorBoard if you prefer. The fit method will return this object, history, that has lots of things that you can use. So it has the loss values, it has the metrics that you specified that you wanted to use when you compiled the model, and so you can also take this history object and plot whatever data you want from these metrics that will be registered there. So if you don't want to use TensorBoard, you can use the history model for that, the history object. So basically what you're going to do is you have a simple first exercise where you're going to re-implement the miles per gallon problem with Keras, just to see how easy it is, but you're going to create this convolutional network for this fashion-ness problem. So each image is in a different class, like trousers, shirts, pullovers, things like that, and you need to classify each image into the 10 different classes. The size of these images is the same as MNIST, 28 by 28 grayscale images, and you do basically the same thing. You can import this data set from Keras. The first time you call load data, it will download the data set into your hard drive. Afterwards, you just load the data and without a problem. And then you just need to reshape things in order to fit them into the convolutional layer. So you have images of 28 by 28 with one channel. This is the grayscale channel. And you have as many as your data set. So basically we are doing this, we are normalizing the values, because these are integers from 0 to 255. We normalize this, and we can even typecast this as 32 bits, although Keras will take care of that. We don't need to create the tensors here or whatever, those things that we did when we were using the basic functions in TensorFlow. And also we need the labels. So remember that these labels are in integers between 0 and 10, but we have a softmax activation that gives us a vector of the probabilities of belonging to each class. So we need to have our classes one-hot encoded. And we use this two categorical, like we did last week, to convert the 10 different classes into vectors of 10 values, with a 0 everywhere and a 1 on the correct class for each example. So after you do this, you can create your model using the Keras API, those examples that I showed, those snippets of code. And the idea is to create a model close to this kind of architecture. If you want to experiment, you can change, but you're going to start with 2 convolutional layers with 32 filters each, rectified linear unit activation, and you can use batch normalization after ReLU to speed up training. And then after these 2 convolutional layers, you add a max pooling with 2 by 2 on the window and the stride. So you're going to reduce from 28 by 28 to 14 by 14 by doing max pooling. If you want, you can try to add a dropout layer after pooling, but remember that dropout in convolutional layers, it's a bit strange. Don't use a large probability, maybe 25 or less, but this is optional. You can experiment to see how it works. I think it works better without dropout, because you are just hiding parts of the image, and in this case, that's not a good idea. Then for the second stack, you do the same thing as the first, but you use 64 filters instead of 32, and then you move on to the dense layer. Remember, you need to flatten things before going to the dense layer, and remember that you also have max pooling. So it's a stack just like this one, but with 64 filters. And then you have this dense layer and another with So 512 neurons, and then the one with the softmax activation with 10 neurons. You can use the stochastic gradient descent optimizer, or you can try, for example, Adam or RMS prop or things like that. Adam would be probably the best first choice, but check if you have convergence problems. SGD is safer, although slower usually. And then you can experiment, change the architecture, change the optimizers, well, do some experiments a bit. And the goal of this exercise is that you understand what these things are that you're using. So it's very easy to use the sequential model in Keras. So you're just like doing a cake with different layers. You just add the layers on top of one another, but you should take care to really understand what the different layers are doing, because otherwise you can easily mess things up if you don't know in which order to put them or what they are doing in your network. So this would be the main goal of the exercises today. Keras is easy to use, but it's important to understand what you're doing. Okay, so I talked too much already. What we saw today was just a brief introduction to convolutions and convolutional neural networks and how to use them for classification. We're going to also look at using convolutional networks for segmentation, and probably your first assignment will be a mix of the two. We're going to talk more about that next week when I finish everything up. So chapter 9 of deep learning is about convolutional networks, and look at the documentation and the examples in the API guide. So the documentation online. This is very important because you need to see what arguments you need to send to the different classes and really understand what you're doing. This is not difficult to use, but take care to understand what are all those values that you're giving to each of the different layers. Okay, so I'll log into Zoom for some questions if you want to, or you can also start on the assignment if you want, because we are already a little late, and I'll keep an eye on the Hangout. Okay, see you soon.